thing. So you have to be very careful when you compare all these numbers. So the ones I'm going to show are all coming from X-ray diffraction, and in X-ray diffraction, you're looking at long-range correlations. That's what we see in Bragg peaks and related signals. So we are looking on the longer length scale, not the local one. And this is also the reason why the onset temperatures and other quantities we find are smaller than what other people find. So this you have to keep in mind. But it's not necessarily a contradiction. So I think the results still are lining up. It's just that you have to keep this in mind. And then we look for the effect of various parameters on this melting phenomenon. One is morphology. That's the first one. I'm going to show, is it really important what kind of stuff you have on the other side of your ice when it starts to melt? Then we use a probe. The question is, of course, always, what does the probe do to the ice? Is there any influence of the probe itself to the ice? It turns out there is. We're using high energy radiation. That means we can break bond and do some other stuff to the ice. And that certainly has an effect. The question is, does it influence the melting itself? It turns out it does. Then we look for the influence of electrical fields, where in a naive way you would say, maybe there is none, because you need quite a high field strength to do anything to the water. But it turns out that's also not true. And then we were studying in the end, I hope I have time to come to that, because that's probably the most intriguing part. We've studied some electrical properties of this quasi-liquid, and they're by no means what you would expect from that stuff. Okay, so let's start. So what's water? Water is very simple. It's composed of water molecules. Normally, in our normal environment, we have water in two different forms. It's in a liquid form and in the form of ice. Ice 1H, which is the hexagonal form. And the only difference between them is of course, one is water, the other one is not. But there's a slight structural difference. This bonding angle here is changing. In the liquid, it's 104.5, and in the ice, it's 109.5. The water molecule has an electric dipole moment. Magnitude is given here. And it's macroscopically not polarized. So there's no macroscopic electrical dipole moment in the water. It means the dipoles are all disordered. Now, when you look at the structure, it becomes immediately apparent why that is so. It's a hexagonal structure, so it's the lattice here. If you cut through this, you find that the water molecules are oriented many different ways, and if you have a dipole moment lined up in this in many different directions, then of course the average is 0. So ice 1H is the only known stable form at normal conditions. If you go high up in the atmosphere, some people claim they have seen cubic ice at very low temperatures. You can also produce it if you deposit vapor directly onto some very cold substrate below, I think it's 130, below 130 Kelvin or so. You find cubic ice as well. There's a whole host of stable structures known when you increase the pressure. So that's the polymorphism of ice, and that is something which distinguishes ice from many other elements or simple molecules, that it forms such a host of crystal structures. The hexagonal ice itself, you can build up a crystal like that by following two very simple rules. The distribution of the protons have to fulfill the so-called ice rules, that you have two protons or hydrogen atoms belong to each oxygen atom, and there's only one proton per bond. That's enough. Now, when you look through all these ice phases, you see that there's essentially every structure there. There's a rhombohedral, monoclinic, tetragonal, cubic. Densities vary over a very large range. There's 2.79, normalized at 0.92. So densities also vary very much. So the question is, where does all this come from? What makes ice so special? Well, there's an additional thing in the hexagonal ice. Although it's a crystal structure, there's already some disorder in there. That's the rotational disorder. So these ice molecules actually can rotate. This is an intact water molecule with intact hydrogen bonds, but of course they can rotate, and that gives rise to rotational disorder, that of course has entropic effects and so on. So that also makes ice more complicated. But when we look at the properties of ice and water more close to ambient conditions, there is something which is really striking. When you look at the response functions of water in the, let's say, in the liquid phase and in the supercooled phase, when you go below the melting point, all of these response functions are harmless. There's not a single one which behaves like a normal liquid. We pretty much know what a normal liquid should do. So all the properties of ice are strange. Whatever external parameter you apply to the system, it responds in a way which normal liquids don't. So, for instance, when you look at the compressibility, that means if you apply pressure, a normal liquid would just follow a curve like that if you're far away from the critical point. And, well, water does this. It initially, when you decrease the temperature, it seems to follow this trend, but then all of a sudden it starts to take off and rise very strongly. The heat capacity is doing the same thing. Thermal expansion, similar. So normal liquid would be just boring, very simple monatomic behavior, but here you can see that this is very different. This is also very different. So every property we know of water is strange. So where does this come from? Well, the properties of water, which are related to these response functions, are really the basis of life here, and one of them has been mentioned this morning, and that is the density anomaly, and this anomaly in the thermal expansion coefficient, which is very important for erosion, for instance, which you need to set the nutrients free for life and so on, because otherwise it would be just a piece of solid rock and nothing to grow on. But ice or water is actually doing all the shaping and reshaping and helping to set the nutrients free, which life needs. So these properties of ice come in a very fundamental way. So the question is that somehow reflected in what we are interested in? That's the melting, and it turns out it looks like it's reflected in that, and we actually get access to these anomalous properties, and maybe can even understand what we have here. Now, the way we get access to this phenomenon, or to these surfaces and interfaces, when we study them deeply buried into some material, is we use a probe that's high energy X-ray scattering, which is very penetrating, so we can look at interfaces which are almost arbitrarily deep in some material. So, for instance, I could use this glass here with the water in there, shoot my beam in there and do some experiments. Just put a sample in there and do the experiments. I can go through centimeters of material, look at a single interface, and still have atomic resolution without destroying it. And that's really different to most other probes, these structural probes. They're all destructive. So, for instance, if you want to use an electron microscope, you have to cut the thing open, thin it, or do something to it that it gets thin enough that the electrons can actually get through and give you an image. But that's altering your sample very much. You could never do that with ice, for instance. So we need something where we can look at these samples without destroying it in any arbitrary environment. And the ideal probe for that is high energy X-ray scattering. Well, the reason is, of course, as I mentioned, or I started to mention, is that electrons are a very strongly interacting probe, so you can only go through a very, very small amount of material and still get a simple enough to interpret signal that you can actually get something out of it. If you go to a thick slice of material, there's nothing you can learn on the atomic level, because you have so many multiple scattering events shuffling intensity back and forth that you lose all the really fundamental information you like to get. So that doesn't work. Neutrons, they have penetration. They do not alter the sample because the interaction is weak. But on the other hand, the reactors we have to produce these neutrons, they have a very low resolution, low flux, and very large divergence. That means there's never enough neutrons to look at anything at an interface at this very, very small amount of material. At an interface, this nanoscopic dimensions, there's no way. So the only thing left is X-rays, and they have nice properties. They have largely tunable penetration. We can achieve very high resolution, very high flux. They interact very weakly. That means we usually have scattering cross-sections which are easy to interpret. It's very simple, actually very simple models. And we have very good sources. We have the synchrotrons, which have boosted the intensities which we have by many orders of magnitude. So this is the right probe. So an example here, when you take different materials like water, silicon, copper, or lead, and look at the extinction, the attenuation coefficient, that's the coefficient which goes into this exponential function here. Within a smaller range of energies, let's say you change the energy by a factor of 2 to 5, you can vary this coefficient by orders of magnitude, and that goes into an exponential function. So you can tailor this beam to almost anything you want. From well, penetration of nanometers to penetration of centimeters, or sometimes even more, depending on the material. So where do we get these X-rays from? We have, unfortunately, to go to large-scale facilities. In the one where I'm going is the ESRF, the European Synchrotron Radiation Facility. That's a large-scale facility, so this thing is more than a kilometer. And it's located between two rivers in Grenoble, supplying us with a very brilliant X-ray beam. And there's a special experimental station or beam line, we call this beam line, which is dedicated to the production of high-energy X-rays, and I've built a dedicated instrument there for surface and interface scattering. And this instrument can be used to look at almost any interface. It could be a solid-solid interface, solid-liquid, liquid-liquid, it could be liquid surface, whatever. It doesn't matter which kind of interface you have. So if you have any sort of interfacial problem, we can actually look at it with diffraction here.
So, can I just ask
yeah?
From the attenuation curve?
Yeah.
You can go up. Your X-rays are bright enough there at that facility to go all the way through that scale. Those were experiments.
Oh, I can go much higher if I want. I just don't want to. Normally. The reason is when you do a scattering experiment, the angles become smaller and smaller as the energy becomes higher and higher. At some point, you can't resolve it anymore, and your diffraction equipment has to be so accurate that you reach a mechanical limit. So I had to build special instrumentation for that. It's a 6-ton machine, and this is more accurate than any other machine of that size. So for instance, this is a 3.5-ton sample manipulation stage, and it stabilizes the sample to 100 nanometer size. And we can control angles to a 10,000th of a degree with this machine. We can host any sample environment up to 500 kilograms, so we can put heavy magnets, UHV chambers, cryostats, whatever. So this is why I'm saying we can look at any interface. Ice, in a way, is not so demanding. It is demanding, but not in those terms. This is a special optical element that we can also look at liquid surfaces. And well, it's a so to say, it's a.
Can I ask maybe a pretty basic question, but I mean, if you prepare a sample with, say, a grain boundary in the middle, you still have to get into your sample chamber.
I come to that point.
Make sure that you scatter off the right surface.
I come to that point. So this is the oh, it's too slow. It only goes back. I see. It's the instrument. Actually, I took out that slide because otherwise it would be too much. Well, the reason why we need this penetration depth to actually look at these interfaces is a very simple one. Normally, when you do a diffraction experiment, what you do is you have a sample and then you have something in there, let's say an interface or another one, whatever. You want to study what's down here, you have to penetrate from the top side and scatter off this way. That means you're collecting also scattering signals from here and from there. And this is very bad, because you're ultimately only interested in this one, and it gives you a lot more parameters to deal with. In many cases, you can't really extract what you want to know. So, but if you have the penetration power, you can actually make a big sample and bury your interface all the way in there, coming from the side like that. And with high energies, you have to come in at very shallow angles, sometimes as small as 1/100th of a degree. And then you see only this interface. And this is not producing any scattering because it's normal incidence. Same on this side. There's no scattering on this side. So you have signals, and that's what I'm showing today, where all the information is coming solely from the interface down here, from nowhere else. There's no stray signals from other interfaces, surfaces whatsoever. And that's the beauty of it. You really see only what you want to see, and nothing else. Well, now let me come to the surface melting of ice. Well, we've heard it's very important for many things. Sintering of ice and snow, charging of thunderstorms. This has not been talked about. I won't touch it today. We'll just accept that. If you want to know more about this, you read John's review. Frost heave, which we have heard today. Then it's also important for ozone chemistry or atmospheric chemistry in general, because the temperatures in the higher atmosphere are actually such that that liquid layers on small ice particles may play, or most likely do play, a big role in the chemistry there, because in these liquid layers, if they exist in the ice particles, they have a much higher solubility, and then they of pollutants in the air, and then you can trigger reactions in this liquid which you couldn't otherwise. So, melting of ice. We've also heard, I can go quickly through this, there's two ways to melt ice. One is the normal thermal melting, the other one is the pressure melting. We have a negative slope in the melting curve, that's the slope, so you can use either one of them. So today we stick only with this, we don't apply pressure. We're not interested in pressure melting here. What do we know about the free surface of ice? Well, this has been studied for decades now, with almost any available probe, and they uniformly agree there's surface melting. Now what I'm showing you here is just one particular probe which probes a particular order parameter and which gives particular numbers for the temperature when this melting sets in and for the thickness which you get. And it's X-ray scattering. Well, the current description we have of this melting process does not really provide a real microscopic picture of what's going on the level of molecules. There have been various mechanisms proposed, like the original Lindemann criterion. That means when the lattice vibrations gets too big, it's usually somewhere in the range of 10 to 14% of the nearest neighbor distance, then the bonds break and the lattice is destroyed and it melts. Franklin suggested that point effects play a big role. Cottrell puts the emphasis on line defects, and there have lots of other mechanisms suggested. But one defect we have in any sample of ice we know of is surfaces and interfaces, because they have a finite size. They're not infinitely big. So this is a two-dimensional defect, and that's a defect which is always there. So there's no way around this. That's the biggest and most common defect. So that's why we look at these interfaces. So you have ice in contact with something, could be a solid, could be vapor. Then you have, in a very simple continuum description, you have a surface energy between the two. Now at a certain temperature, now we've heard that this morning already, it might be better to actually have another interface between those two and put in a liquid wedge, so to say, in between, and that still lowers the total energy, although you have the price of the latent heat, which you have to put into the system to actually turn the ice, this ice piece into a liquid. So it's still better because you lower the interfacial energy in a certain temperature range. Not for all systems, but for some.
Harold,
yeah.
Before you go on, are you going to say anything about Lindemann, or was that it?
That was it, because that's not my main point.
Can I just say something before you go on there? Lindemann's theory is flawed on a whole hierarchy of levels, but mainly it's because it's a one-phase theory of melting. It looks only at the solid phase and says when the mean square vibrational amplitudes exceed some critical threshold, then something melts, but you can't have melting without coexistence. And so that theory set people off into the wrong direction, measuring Lindemann parameters for a long time. And it's actually your conclusion that all crystals are finite and have surfaces, which is important. But if you look in the literature, you will find papers on the Lindemann criterion for melting of infinite solids. And we have yet to find an infinite solid.
That's right.
Yeah.
Well, actually, for our purposes, what we look at is the free energy of this of the thing which you have seen on the last slide. And there's essentially these terms here. There's the latent heat which you have to put into to melt the ice. There's the interfacial energies of the two interfaces, if you have them, and a possible interaction between those two interfaces, if there is any. Now let's suppose we had an interaction and it's short range of this form. Then the interfacial free energy looks like this, and we have seen this already, with a minimum for some finite temperature. Now as you change the temperature, the shape of this curve will change, and this minimum, the location of this minimum will change, and you get a certain curve for this. And as a physicist, I would not do it this way. I would just take the derivative and look at it, and then you get a growth law. And in this growth law, you only have two parameters. One is the temperature of the onset for the melting, and the other one is this L0, which is essentially nothing else than a measure of the correlation function in the liquid. So you learn something about the structure of the liquid as well when you study this. So this would look like this. You plot the temperature on a logarithmic scale and this on a linear scale, and you get a straight line. Now if you had different kind of forces between these two interfaces, let's say of a more long-range type, van der Waals type, then the shape of this curve changes. That part stays the same, that one is changing. That means the minimum position here is changing. And if you derive the growth law for this one, you arrive at a different one. It's typically a power law with some exponent n, which is related to the decay of those forces. You can think of this this interaction like a disjoining pressure, it just pushes the two interfaces apart. And this has a different shape when you plot it the same way. It increases much faster than the other one. Now, in a real system, you would always, even if you start with very strong short-range forces, at some point, if you get far enough away, these forces are gone, and then the long-range part takes over. So there should be always a crossover in the growth law. Even if you start out with something which is logarithmic, at some point, if you go high enough in temperature or close enough to the melting point, you should always get to something like that. And that has actually never been really seen. So, what do we know about the free surface of ice? I've said I'll touch this only very briefly, and this is the results as they are seen by wide-angle X-ray diffraction, which was done more than 15 years ago in our group. And what you see is that there's a relatively thick layer developing here. These are three different phases: the basal, the prism, and one in between. And what you also see when you go close to the melting point, there seems to be something else going on, because the thickness all of a sudden starts to increase much more. And all of these phases melt. And that is something which is very peculiar, because we've heard that lead and other metals also show surface melting, but they show this only on certain facets. And these are usually the facets which are not so densely packed. If you take lead, it's the 110 phase. If you take aluminum, it's the 110 phase. In any cubic material, it's typically the 110 phase, the others don't melt, like the 111. It's a close packed surface where the atoms do not have too much space to move around, and they stay solid as much as we know. Water or ice is the only material we know where every surface melts. In that respect, this is really particular here. Now, when you look with X-rays, where you look at long-range order parameters, in this case it was Fourier components of the crystalline lattice which have been measured, finite Fourier components, you see that the onset is around -30, -50 degrees. It behaves as a wetting phenomenon, so it grows in a logarithmic fashion until you get very close to the melting point. And what we also know is that the translational disorder, that's what we measure here, is preceded by rotational disorder of the hydrogen bonds. That was another experiment which was done in our group. It shows that long before the translational order sets in, rotational order sets in.
But that T there is reduced temperature.
That's reduced temperature. And from this experiment here, when you look at the pre-factor, this is rather large. This is 84, 42, maybe you can't read it so well, it's 36. The correlation length in the quasi-liquid seems to be much larger than in white water. That was something which was puzzling me for a long time. I still don't have an explanation why this correlation comes out so big. It's actually at least an order of magnitude larger than what we have in white water. But let's for the moment assume that we understand this, and this is what the free surface is doing. Now, we were looking at deeply buried interfaces because it's actually very difficult to do the experiment at these free surfaces, because first of all you have to keep the angles stable, and then there's always material removed by sublimation, and then later on, if you don't control the humidity very carefully, then recondensation, and this may change your surface. That gives you all sorts of problems. So you avoid that if you put some other material on the other side. We just took silicon, highly polished silicon with a native silicon dioxide layer on it, take our high energy X-ray beam, focus it to a few nanometers, and we do a reflection experiment. Now in this case, we are measuring the zeroth order Fourier component, and that is only telling us what the density is doing. We are not seeing the lattice actually melt. We only see a density change. Now, that's similar to what we do in ellipsometry. We don't see the lattice melt, we see a change in density. Now suppose the lattice melts and there is no change in density, we wouldn't see it. We would get no signal whatsoever. It could be liquid, as long as it has the same density as the ice or the solid on the other side, you don't see it. Yeah? If you measure the zeroth order Fourier component. That would be a curve like this. So you would only see the smooth decay of the reflected beam with momentum transfer as you will have it for a single sharp interface. That would be something like this blue curve. Now if you have a layer developing in between with a different density, meaning a different index of refraction, then of course you're not only reflecting at this bottom layer here, but also at the top one, because there's another jump in the index of refraction. And these two beams interfere and they give you an oscillating structure like this. So this is the telltale signature that there's a layer with a different density. Yeah? As I said, it could still be melting, but if there is no change in density, we don't see it. So this is what we have, the experimental system and condition. We had very good temperature stability in these experiments, down to millikelvin. This was actually a large chunk of ice, so it took some experimental skill to stabilize all this. We use very small beams. We can access a very large dynamic range here, 10 orders of magnitude. And then we can do the experiment. Now, what do we find? Well, and this is about the only curve which is published. What we find is this: if you start at low temperature, -25 roundabout, there is not much structure on this curve. It pretty much decays like a Fresnel curve. There's only a slight bump in here, and we know where this bump comes from. That comes from the density change in the silicon dioxide. There's this native amorphous layer of around about 2 nanometers there, which is producing this bump. This bump is only very slight because the density change between silicon and silicon dioxide is very small. And then as you increase, you see there's this oscillations coming. There's nothing else changed in the experiment, only the temperature. And we interpret this as the emergence of a layer with a different density. And, well, we think it's melting. And you see this thing gets thicker and thicker because the oscillations get shorter and shorter period. That means it gets thicker and thicker. Because what you're doing here is nothing else than a Fourier transform of the real structure. Far-spaced oscillations means thin layer. Close-spaced oscillations means thick layer. So you see the layer growth here. Now this was, when we did the experiment, this was fully reversible. So for instance, if you sit here at -0.5 degrees, you see this signature of the layer here, then you increase the temperature. You go closer to the melting point, 36 millikelvin below, and you see much closer spaced oscillations. That means much larger layer thickness. You go back and you get exactly the same curve back. So this is fully reversible. That means we are in thermodynamic equilibrium. So now this was the first experiment. Now later we did the second one where we thought, well, maybe this depends on what the interface looks like. There's a morphology to the interface. Does that have an influence? Well, we had a rough substrate then, and this is the smooth one again. And you repeat the experiment. It looks, if you look from far, it looks pretty much similar, but in detail, it's different. When you look at the fringes, they're different. The onset temperature is roughly the same, but the oscillation strength is a little bit different. And if you go to the same temperatures, the spacing of those fringes is different. So that means morphology seems to have an influence. Now I skip that one. Now what would you expect when you do an experiment like that? We have a probe which in principle has molecular sensitivity, so we can see a single molecular layer, one monolayer of water or ice with the piers. Now initially, you would expect when this starts to melt, it would at some point melt the first layer, and it would be a discontinuous process. You start melting the first layer, then you melt the second layer, the third, and then at some point it starts to be more continuous, more like this. And then it, in principle, can have this growth law can actually follow two different regimes. If they are short-range forces, that means they must be important when this layer is thin, and we would have a logarithmic law for the increase of this layer thickness, which later on has to go into a power law, or if this is not present, then it would be a power law right away. Now let's see what we find in the experiment. When we take the smooth one, that's as observed, and plot this in this semi-log plot, you see this follows very nicely a straight line. Down to, this is a double layer. This was the resolution we had in this first experiment. It's just a double layer of water molecules or ice. That's when we see the surface melting sets in. Now, of course, we can now fit this power law, and the prefactor we get, this 0.41, is very nice now, because that's the biocorrelation length of water. So we're really seeing something what we understand to be water. Not unlike what we had in these free surfaces, where we have a prefactor which is pretty much 10 times bigger, and which I still don't have an explanation for. So we see a logarithmic growth law, and the amplitude which we see in there is very much comparable to the biocorrelation length what you would actually expect. Now if you take the rough surface, and that was what we initially did, these are the data points here, these squares, and you fit this, you can fit it somehow, you curve like this, and you see the only difference you have is that the correlation length gets twice as big. Now why would the correlation length of water change if you make the surface somewhat rough? Why should that affect the water? So we reinterpreted this curve in the following way. Let's assume now this is the smooth interface. That initially it follows the same curve. So let's say up to that point, roughly -1 degrees centigrade. It's the same growth law. It fits very nicely. But then all of a sudden it starts to take off, and then of course you can fit this with a power law. It's only a few points. It's only 5-6 points, so it's not too accurate. But the numbers we get are pretty much what you should have for a system like that, which is dominated by van der Waals forces. We get n is equal to 2.34 from a fit. Actually, the theoretical value would be 2.3. So it's very, very close. And in the prefactor, and I haven't mentioned that before, in the prefactor for the growth law, in the logarithmic case, you have the Hammacher constant, which is this one. So, and again, when you do a fit like that, you would expect to find something water-like, and that is actually what we get. The value we have here is the Hammacher constant for water. So this fits again. This looks like it's a nice consistent picture. Now, why would at a rough interface the growth law change from logarithmic to power law? That's a good question. Why should that happen? Well, there's actually one mechanism which could do that for us, and that is if you have an interaction which is non-linear between these two interfaces, which is the case for both types of interactions, then if you have a rough interface here, and even in the case that this is fully conformal, so that locally you always have a very well-defined layer thickness and which is always the same, the interaction you have between these two interfaces is altered. And the reason for that is that if you sit on a protrusion here and you want to know what the total interaction is with the other side, you actually have to integrate over all components coming from this interface. Now, if this is sitting closer to, let's say, another protrusion over here, then this distance gets shorter. So that means, since this is a nonlinear interaction, that you're not just averaging here, you're changing actually the average interaction is not just in the middle here, but it's somewhere else. That means you're changing the repulsive part of your potential. You know, this interaction potential between the two interfaces. You don't change the attractive part, but you change the repulsive part. And what does that do? It shifts the minimum towards larger thicknesses. And that's exactly what we see here. Now, how big a change do you actually need here in this to get something like this? Actually, not very much. I've shown you that, well, in the experiment, let me go back here, when you have this curve here, initially and the smooth interface, we go down to, let's say, 10 millikelvins, close to the melting point. So that's actually pretty close to the melting. 10 millikelvins is not much energy. It's a few millielectron volts away from melting. So it means if something like that happens, it doesn't need much shift in energy to actually have a mechanism like this kicking in. It's only a small shift in energy you need to actually do that. That's what I think what happens here. By introducing this roughness, and it was a very particular kind of roughness we had in our experiment. This was a so-called self-affine rough surface. That means there's roughness on all length scales. So if you plot this as a correlation over many length scales, you'll find it's on all length scales, from the small to the large. And the energy shift which this requires is less than 0.1 millielectron volt. So that's really something I think roughness can do. It's a very, very tiny energy shift you need for that. It's not very much. And I believe that this is mostly due to the change in the repulsive part of this potential. I think I have to hurry up a little bit. What other experimental evidence do we have? Actually not much. There's not really many quantitative measurements of interface and melting. The maybe best one I found was from Beagley, Hall, and Wilson in '94. This was an ellipsometric measurement on smooth and rough glass substrates which have been treated such that they were hydrophilic or hydrophobic, with and without impurities, and they did not find interface melting for the smooth one without impurities or for smooth hydrophobic interfaces. But when they had a rough glass substrate with impurities, you see something like that, and you see that is really different, because within a few Kelvin here, this is jumping up to 2,000 angstroms. Now, this is a double log plot. When you look at the parameters you get from this, the parameters for this liquid layer again are nowhere near water-like. So this is really not just a molten water layer you see here. There is something else in this experiment. Of course, it hasn't been quantified, so I can't really say what it is. The only thing I can assume is impurities. There's nothing else which can change the parameters so much that it's so far away from anything you would expect for pure water. Now there is another thing we have to talk about. I told you we wouldn't have any signal if the density wouldn't be changed, and that is something that was the real killer for us at the time. These are now the values for the density in that liquid layer, the average density, as a function of temperature here, and for the rough and the smooth surface. So you see there's some scatter, but there's really no difference between the rough and the smooth surface, and that's actually what you would expect. Why should the water be different when the surface is somewhat more rough or smooth? Now, if you plot this in a different way, that you take the temperature dependence of the layer thickness and plot the density as a function of layer thickness, you see this looks actually different. This is a fit to it, a linear fit to it. You see that there's a gradient in this. There's a slope here, and then it's more dense when the layer when the layer thickness is thin, and then it gets gradually down, which it actually has to do, because if you go to a very large layer thickness, ultimately you must have bulk water. It can't be different. Now, let's look at the value. This value here is actually very large. If you go to the thin layers, 1 or 2 nanometers, you are at a density of 1.5 gram per square centimeter. So this is not bulk water whatsoever. It's a very different density. So what kind of water is that? It was something we were struggling with for some time, until I was digging a little bit more into literature and looked at the phase diagram for water again. Now, there is a struggle in the water community since well more than 10 years. Ever since Angel and others and co-workers brought up this suggestion that water actually has a second critical point in this region, which is called the no man's land, because you can't go there with a bulk sample. Why is that? Well, this critical point lies below the temperature for crystallization. So you can't super cool water to that point. It will always crystallize before that. But if you could, you'd actually see there's a second critical point, which is the terminal point of a line which separates two different phases of water. High density water and low density water, which are the vitreous equivalents of well-known amorphous phases. We know there's a high density amorphous phase, or very high density amorphous phase, and a low density amorphous phase. So there are two distinct structures. And if you freeze this, it should actually give you also two distinct water structures. These are just the vitreous counterparts to what's here. The only bad luck is, so to say, you can't get there. So you can't really make these phases of water. Now, all these anomalous properties of water are actually thought of being results of the fluctuations in this regime around the critical point. So you have large density fluctuations there, and they are responsible because this is actually all which goes into these response functions. It's the density-density correlation. Yeah? This correlation function that determines what the response function looks like. So this could actually be the explanation for that. Now that means there should be two distinct water phases. Now if we have a system, let's say a bulk system, and if we could supercool this to this temperature, then this system would, at the according pressure, separate into these two. But if you are above, you can't distinguish between the two, and the system only shows large density fluctuations in this region. Now if you have a surface which prefers one fluctuation over the other, or a certain phase of the fluctuation, and pins the phase, you actually can collapse this two-point density correlation function, which we have in the bulk, into a one-point density modulation. And that's, I think, what happens here. Our surface simply favors the high density fluctuations of the water, and we stabilize them with this additional interaction which we have at the interface. That's the current understanding we have from that. So in that sense, you could interpret this as an indirect hint that this second critical point scenario is not all that wrong. But this is an ongoing debate in the water community whether this second critical point really exists or not. This is still an open question, and a very important one. Now I told you that we have a probe which is actually interacting with a material, and we have very, very high intensity in our beams. That means you have to ask yourself, what does the radiation do in all this? Is there, for instance, radiation-induced melting, or is it all thermal, what we see? Well, for this, we did experiments on many different samples. This has taken quite some years. We looked at, so this is now all SiO2 based, but we also looked at other materials like MgO and others in various forms, because we know that the morphology is important. And morphology means now not only roughness on a large length scale, it could go down to the atomic length scale, where you have epitaxial effects between the ice on one side, which is crystalline, and some underlying crystalline material, which also has a structure. And this could be compatible or non-compatible. So we took silica, because that's disordered SiO2, we took quartz, which is a single crystal, and then we took glass, which has been processed in a different way, that's so-called float glass, and did experiments on all those, similar to the ones which I've shown you. And the one thing we noticed when we did these experiments, in one of them, we actually illuminated the sample for a long, long time, and repeated the measurements again and again. This is now at -1 degree centigrade, where we should have surface melting, and what we saw, or interface melting. And what we saw is that those curves change with time. Well, that's a telltale signature of radiation effects. That's for the ice-silica interface, this is for the ice-quartz interface. These are the reconstructed density profiles. And when we look at the density, we retrieve the densities which we have seen before. So this does not have any effect on the water structure, but it has an effect on the thickness, as you can see. So the longer you irradiate, the thicker these films get. Now if you plot the layer thickness versus temperature without taking this into account, you're left with this puzzling fact that you have lots of points for the same temperature, so you can't really fit a growth law to this. So these are 2 points here, 3 points here, 2 points here, and so on. So there must be some other effect triggering or influencing the melting. Now if you take the data points we have, and initially we didn't know that, because otherwise we would have just kept going on increasing the radiation dose and take more data. But if we take the data we have and actually plot them linear, the thickness versus the radiation dose, we see that all these layer thicknesses increase with radiation dose. And then of course you can, in a linear fashion, you can correct for this and take the growth laws which we had before, these were the other experiments which I showed you, and correct for this with a linear term, and then you see that they fall relatively close or close enough to this logarithmic growth law as they should. So that means there's a second way, or third way, to trigger melting. One is pressure, the other one is thermal, and the third one is radiation, damage. Now we have to pump in. The radiation doses we actually use are huge. When you look at this, this is, let me go back, this is mega gray. These are huge doses. And the reason why we need such a huge dose is that the interaction of these high energy X-rays is very small, so you have to throw in a lot of photons before you do significant damage. If you would have radiation, which has much more damaging character, particles or something like that, I guess this would trigger the melting much more. And this might be the case in interstellar media, where you have, of course, lots of high energy particles, which can damage the structure much more than the radiation we have here. So this is a, so to say, a third way to initiate melting. Now I come to another thing, electrical fields. And that is something we got interested in when I saw this paper, which appeared actually, when was it, 90? No, this was 2005, that's wrong. That was 2005. This was a Korean group. And they had an electrochemistry experiment where they had a gold tip, a gold surface, and some electrolyte in between. And what they noticed is when they brought this in contact close enough, you always have a voltage applied between those two. This is a tip, a very narrow tip. It's a very confined water space in here. And what they claim, what they have seen, is that they see solid-like behavior of this water or ice or whatever it is in between when they increase the field strength above 10 to the 6 volt per meter. Now, when you think about what electrical fields should do to, or how they couple to the water molecules, that's of course via the electrical dipole moment. From simulations we know, or it has been estimated, that the field strength for aligning those dipoles and bringing them into some sort of structure should be around about 10 to the 9 volts per meter. So that's a huge gradient. That is something we can do experimentally. But surprisingly enough, and that's probably the reason why it appeared in PRL, they saw effects from 10 to the 6 volts per meter on. And that is something which we can do in our experiments as well. We can reach 10 to the 6, 10 to the 7 volts per meter. So we thought, why not try and see what the influence of electric fields actually is on this melting. We did corresponding experiments which were a bit more complex, because first of all you have to isolate the whole system electrically, thermally and otherwise, and that required for a more complex setup where the sample actually sits in here. And we apply voltages between two silicon crystals, which doped silicon crystals, and we have conductance in here, up to 10, 15 kilovolts without having breakthroughs. Now we can reduce this size here to a millimeter or something like that, so we can get 10 to the 6, 10 to the 7 volts per meter. And the question was, what would we see? Would this actually promote melting or prevent melting, or is there any influence of those fields? Well, the experimental results are following suit. Let's see. There was a first measurement, and this was taken right after we put the sample in. That means there was no radiation-induced melting, because there wasn't enough radiation dose yet. That was at a certain temperature. I think this one was -1. And the first one is without any high voltage. And then we turn the high voltage on and measure the structure as fast as we can. So every 5 minutes we can take one of these curves. So this is after 5, 10, 15, and 20 minutes. And what you see is there's a layer appearing. And this is only due to the field. If I switch the field off, it goes away. That's interesting. Well, the field we had, or the voltage we had, was only 150 volts. Actually, we thought we had to apply something like 15 kilovolts. That's what we started with. Found out this was way too much, so we went down to much lower electrical fields, and we still could do significant effects on this molten layer here. Now, when you look at the reconstruction of the density profile, you see now that this looks different. Now, you can fit this only with a 2-layer model, where you have one layer which is more dense. That's again the same density which we always find, is 1.25, followed by a thicker layer which has a lower density. Or if you want, because there's roughness there, it's more like a gradient type of density profile in there with a high density layer close to the silicon dioxide again. So that would be the same mechanism, by the way, we just pin those fluctuations. So it seems there's a strong influence of relatively weak electrical fields, much weaker than we originally thought, on the structure and formation of these quasi-liquid layers. And that this is actually, if you illuminate this for a longer time, this was done here, this was after a whole series of experiments, we actually turned the high voltage off, and then, because we have a very tiny beam, the beam is only a few microns in size, we can actually scan the sample underneath the beam and go to an area which has not illuminated, which has not been illuminated so far. And then you see that the signal we get, so we fix this at a certain point in reciprocal space. Here, this was 0.28, let's say here. And then we scan across, and then we see that the signal is changing very much in this point. So we have melting, which is induced by radiation, thermally, and by fields. All three are changing the situation here. And this is so to say the third one kicking in here. This is again radiation, because this region has not been irradiated before. This one we have irradiated for a long time, with and without high voltage. So the one was with high voltage. This was 150 volts, which is not really high voltage. This one with the electric field on and off, and this is what you see on the side, native, which has not been irradiated. So all three of them actually play a role. So there's lots of parameters actually going into this. You can't simply go to the literature if you want to know for a given system how thick this layer could be. It depends on how clean it is and what history it has gone through, in terms of radiation and so on. So you can't really say it's 10 angstrom at minus whatever, 5, 6 degrees. No? It really depends on the history the sample has undergone. So now, last thing is that we wanted to know more about this layer, because we're always talking about a liquid layer. We know the density is not by no means what it should be. So what is it? What kind of water is that? Problem is, the best probe to actually look at that is X-ray scattering, and you would just measure the liquid structure factor. The problem is, for this thin layer we can't, and there's a technical reason why we cannot. And the reason is that when you go back to those pictures of the samples, like this one, we could do this very nicely at other interfaces, let's say a liquid metal in contact with silicon or some insulator or whatever. But we can't do it for ice, and the reason is that the density in the ice is smaller than the density in the solid on the other side. So normally, if you want to have depth resolution, or if you want to get your scattering signal just from that layer, you have to use a trick which is called the production of an evanescent wave. John knows very well how this works. That simply means you go below an angle where the wave, the incoming wave, can actually not penetrate into the system anymore, but is being totally reflected. And in this regime, you implant a traveling wave parallel to the interface in a very thin layer. It's damped into the system. The only thing is that the density contrast you need is such that the density on this side here, the one which you want to see, has to be higher than the density on the solid side. Now, unfortunately, we don't have a solid which we can prepare very nicely and which has a lower density than ice. That's a pity. If we had a solid of, let's say, a density of 0.5 gram per square cube centimeter, and which we could prepare very nicely, we could have done this years ago, but we can't. So this is really a pity. So we have to resort to other means. I can't measure the structure factor here. So what we actually did, then, oops, I have to go a little further. So that's here. We use something completely different. Well, one way is we know the density is different, so the structure has to be somewhat different. The question is, are there other properties affected by this? And the first thing we thought we could test was the electrical properties, and for this we used a scanning Kelvin probe. This is a very old technique. It's called Kelvin probe because it was invented by Lord Kelvin. And all you do there, the principle is very, very simple. You have a sample, you have an electrode, and you put this to the same potential, and you can simply measure the work function you have between the surface and the tip on the other side, or the reference electrode here. That's a very simple thing in practice. When you want to, if you want to do this very accurately, that's the machine. It's not so simple. You have to work in with lock-in amplifiers and a couple of other things. But in the end, if you build such a system, you can actually measure the work function of a sample like that, and that is what our sample looked like. This is all rather new. This is why this looks not so sophisticated yet. So what do we have? The sample actually looks like that. We have a copper block, which acts also as a heat exchanger. Then we have a silicon wafer, which is gold plated to have electrical contact on the back side. Then we have ice on top of it, with maybe an interfacial liquid layer and a surface molten layer. So there might be two quasi-liquid layers here. And these are, of course, connected and kept at the same potential, which is just the Fermi potential. Now, when you look at the potential across, across this whole stack of layers or materials, you might be looking at just a sketch somewhat like that. So the potential here, the electric potential across this interface may fall. Then you have an interface between the silicon or silicon dioxide and the quasi-liquid, then the quasi-liquid and the ice and the quasi-liquid, and so on. Then there's the gas phase, and there's the reference electrode. And what you measure is the sum of all these changes as a sum signal, which is giving you this here, this difference. That's the work function you measure. So you don't see these individual steps and jumps. You just see the combined action of all these. Now, if you do an experiment where you change one parameter, and where you know the only thing which is changing is one of the interfaces, then you can actually assign the change in the work function to this particular interface. And that's what we try in this experiment. Apart from the fact that we have two quasi-liquid interfaces here, most likely. Well, this was the first experiment we did. This was just a trial, so say a long shot. You measure this signal here, which is nothing else than a voltage. As a function of time, you change the temperature in between it and keep the temperature at constant for some time. And what we see here as we change the temperature is that we do a temperature change, then this work function here relaxes after some time and stays at a plateau value. And then you change the temperature again, it gets another value, do it again, and so on. And you get different values. It's reproducible. So, for instance, if you go from -2 to -1 and back, you get essentially the same value. Same over here. So these are reproducible measurements you can do. Now, what do you do with a measurement like that? Well, the only idea we came up with was actually the following. We take the lowest temperature, where we normally say the onset of surface melting is, let's say, -15 degrees. We couldn't go lower at the time with the cooling we had in this apparatus. We take this as a reference potential, and now we measure the difference potential to all those temperatures. So this one, this one, this one, and this one, and plot this as a function, as we did before, of the difference in the temperature between the actual temperature and the melting temperature, so-called reduced temperature. And what you get is this, if you plot this in a semi-log plot. Now this is what we see when we do our X-ray measurements. It's the same thing. Yeah? It's also a logarithmic increase. That's very interesting. Why is that? Because the SKP signal seems to be proportional to the quasi-liquid layer thickness, and that is something you would never ever expect, because what you measure is the surface property. Now you grow this layer thicker and thicker, and your signal is changing accordingly. So what you actually see is a bulk property. How can you see a bulk property with a probe which only sees surface signals? Now that was a big question at the time, but when you think about it, how these signals are actually produced, and we repeated this experiment on, in the second run with a different SKP, because initially I didn't believe it. This was so strange, or so unexpected that I didn't believe it. So we did this experiment several times on different samples using different SKPs, and we always get the same thing. So this is just a different starting temperature. If you add the offset, this was the lowest temperature we started here, which was -3. If you add the offset, which you have here, then you see they fall nicely on top of each other, and they behave as they should. So where does this signal come from? Well, the only way to explain that signal is that there's something in the bulk of this layer which is not, what normal water should be. And then I found a paper which was published fairly recently, where some people in Berkeley, I think, did AFM Kelvin probe measurements at room temperature, where they actually deposit water films on a substrate, silicon in this case, and they measure the Kelvin probe and the thickness by XPS signal, so it's a spectroscopic method, and this potential here as a function of relative humidity. Now, you can use this curve now. This is now the water layer thickness, and you see this is going like this as a function of humidity. And this Kelvin probe signal actually saturates after something like a few layers. So this is 2 monolayers, this is 4 to 5 monolayers, and it saturates. And there's almost no increase here for the thicker layers. That means it's actually doing what a work function measurement should do. It tells you what at the surface happens, and it doesn't matter how much bulk material you add. It has no influence. Yeah? The work function doesn't change if I take a piece of copper which is 1 millimeter thick or 10 millimeter thick. It's still the same work function, yeah? at the surface. So you shouldn't get a signal which is proportional to the thickness. And this signal saturates very quickly with almost no change here in the last 2 monolayers. So most of the signal comes from the first 1, 2, 3 monolayers. But we see that these signals go with the layer thickness, linear, up to much higher thickness. So the only interpretation left for that is that what we actually have here, and this is the only way to produce a signal like that you have oriented dipoles in this layer. And we have no field. There's no field applied. Yeah? So what we think now, what these results indicate, is that in this quasi-liquid layer, you have a uniform dipolar ordering or macroscopic electrical moment, dipolar moment in this thing, which is not what bulk water is. So this thing is really different, not only in terms of structure, but also in terms of its electronic properties. This is really different. It's a really different form of water. And then that's the only thing we could come up with so far to explain that signal. Because we know, I mean, this has been measured in other systems when you have dipoles which you can orient, that these produce signals which are proportional to the thickness of the layer of these dipoles. So this is well established, and that's the only one we could find. So that's really interesting. So this is not bulk water whatsoever. What you see there, this is no normal water. It has a macroscopic electrical dipole moment, which water doesn't have. It has a completely different density, so it's not bulk water. So, and with this, I'm finished. The summary is with our methods now, I think we have access to the structure of these deeply buried interfaces, and I hope you believe me that we can do this with atomic or molecular resolution. We find interface melting in the quasi-liquid layer, as we expected. We find that this quasi-liquid layer has an extremely high density, that the appearance and the overall structure of this is influenced by roughness, electrical fields, and also by radiation. And it seems that this quasi-liquid layer is macroscopically polarized. So with this, I'm finished, and there's a few people I would like to acknowledge. That's of course the students who were working with me over the years. Carlo Dosch, who was supporting this for a long time. My contacts at the ESRF, with whom I operate that instrument. Jörg Pilgram, who gave us the crystals, which we unfortunately all lost, and this is why we were essentially out of business for 2 years. So we have no crystals left, we lost them all. And a nice collaboration with the people at the MPI for iron research on this Kelvin probe stuff. Thank you for your attention.